This video is all about de Moivre's theorem. De Moivre's theorem allows you to take a complex number and put it to a power in a really quick, easy way. This is what the theorem states. That if I have it in modulus argument form at the top line here, then all I'm going to do is take the modulus r and put it to the power n. So I will have r to the power n. I will take the argument theta and I will multiply it by n. So I'll have n theta. That's it. That's all de Moivre's theorem says. Take the modulus, put that to the power, multiply the argument by the power. Similarly, in exponential form at the bottom here, take the modulus, put it to the power n, take the argument, multiply it by n. So put the modulus to the power, multiply the argument by the power. This should hopefully make sense, because we remember that we have this result, that when we multiply two complex numbers, the modulus of that result is equal to the modulus of the individual complex numbers being multiplied together. So if I took z to the power n, that's going to be multiplying the moduli n times, so modulus of z times the modulus of z times the modulus of z, and so on, n times, which will be r times r times r times r times r, n times, which will be r to the power n. So this should make sense. We've also seen that when we're considering the arguments, we add the arguments together. So if I was considering z to the power n, then I would be adding the arguments n times. I would have n lots of the argument, n times theta. So this should make sense. There is a formal proof of this. We'll prove it by induction. We can do this in class. But hopefully these results should make sense. Let's look at a couple of examples using these results then. So here we need to simplify this expression. So I've got cos 9 pi over 17 plus I sine 9 pi over 17 all to the power 5, and I'm dividing that by cos 2 pi over 17 minus I sine 2 pi over 17 all to the power 3. So first thing I can do here, the fact that it's a minus here, let's deal with that. So I know that if I have a minus in my modulus argument form, that means that the argument is going to be negative, like that. Now I'm going to use de Moivre's theorem. So in both of these cases, the modulus is just 1. R is 1 here, R is 1 here, so I don't have to worry too much about that. But I am going to take the arguments and multiply those by the power. So my 9 pi over 17 is going to get multiplied by 5. So that would give me cos of 45 pi over 17. So I'm just timesing the arguments by 5 using de Moivre's theorem. On the denominator, I'm timesing my arguments by 3. So minus 2 pi over 17 times 3 is going to give minus 6 pi over 17. Now I know that, excuse me, I know that when I divide complex numbers, I subtract the arguments. So I'm going to do 45 pi over 17 minus the minus 6 pi over 17. So just to repeat, when I'm dividing complex numbers, I subtract the arguments. So that would give me 51 pi over 17, which is the same thing as 3 pi. So I could write the result of this as being cos 3 pi plus I sine 3 pi. 3 pi though, I can simplify that. If I think about my Argand diagram, 3 pi, well that's going all the way around 2 pi and then going another pi. So 3 pi is the equivalent of just pi. So I can replace this then as being cos pi plus I sine pi. Cos of pi is -1. Sine pi is 0. So therefore, all of this just simplifies nicely to be -1. Okay, next we need to express 1 plus I root 3 to the power 7 in the form of x plus iy. So, in order for me to use de Moivre's theorem, I'd like to be able to write this in modulus argument form or exponential form, either way. So I need to work out the modulus and the argument of this number. So let me draw a little sketch. So 1 plus I root 3 is here. I know that this is 1. I know that this is root 3. So I can work out the modulus of this by doing a bit of Pythagoras, which will give me 2. The argument, if I do tan inverse of root 3 over 1, I'll get pi over 3. So this allows me then to rewrite my 1 plus I root 3 as 2 times cos pi over 3 plus I sine pi over 3. And all of this is to the power 7. So all I've done so far is I've written my 1 plus I root 3 in modulus argument form. The good thing now is I can use de Moivre's theorem. So I can say that this is going to be 2 to the power 7, excuse me, times cos of 7 pi over 3 plus I sine 7 pi over 3. Two to the power 7 is 128. Now the 7 pi over 3, well, 7 pi over 3 is the same thing as 2 1/3 pi, which is the same as going around 2 pi plus the pi over 3. So I don't need to worry about the 2 there, I can just have the pi over 3. Now I just need to rewrite it in the form of x plus iy. So 128 times cos pi over 3 is the same thing as 1/2. Sine pi over 3 is the same thing as root 3 over 2. So multiplying this through, then I will get 128 times 1/2 plus 128 times root 3 over 2 will be 64 root 3 I. And there we go. So by writing complex numbers in modulus argument form, that allows me to use de Moivre's theorem. So take the 2, put it to the power 7, take the argument, multiply it by 7, which then allows me to figure out the result in a quick and easy way.